Oh, yay. May the class come to order. All right, so this is where we left off. Continuing on, and I actually should have moved forward. This here is just going through the month cycles, and I've covered that enough. I do have examples of a couple calendars here that were interesting, but I'm not going to cover them. We do have the Julian calendar that I talked about at the beginning of the lecture, so you've already seen me talk about the Julian calendar, and apparently I didn't get that one resized like I thought I did. Here's that statement. The original may have had 10 months. We just don't know. And here's the leap year thing that we talked about, so we've got that covered. I've talked about the AD versus CE thing. But one thing that I find interesting, I have to go back to graduate school. One of my buddies in graduate school, his fiancée was taking Bible lessons, whatever, from one of our Adventist lay people there in Moscow. Moscow, Idaho, by the way, not... Yeah. I went to school at Wazoo in Pullman, Washington. And so, since it was an Adventist guy giving the Bible studies, why they invited me to come over, and I came over, and he was talking about, we have our years are based on the birth of Christ, Anno Domini, the year of Christ, of his birth, and the BC before Christ. And my buddy, who was, studying for his doctorate in chemical engineering, thought, so did they choose that then? When Christ was born, they said, this is going to be where we set the demarcation? Yep. How'd they know? I don't know. I guess they just did. After he's gone, my friend's all, is that true? I don't know. It doesn't make sense that it would be that way. And now I know because I've looked it up. It was 532 years after the birth of Christ. Remember, AD is not after death, like some people say. It's supposed to be the year of his birth. It was 532 AD that it was proposed that the numbering system... Remember, no food out there.
Okay, I won't eat it.
Was proposed. And I would say that went on until about 2000 before people started trying to change it, cover it up with things like Common Era so that they wouldn't use the name of Christ. But like I said, to me, Common Era means in the age of Christ. Okay, so just to have that number I had in red. Now we're starting new material. A blank or an blank, because some people would say and for hypothesis. I was always taught that if you're voicing the H, you use A. Is well supported observationally and or experimentally. System of rules and principles that can be applied to a wide variety of circumstances.
They click those?
Yep, that's a clicker question.
I think that's the same as Peter.
Woohoo! Satish went and got his clicker.
Yeah.
And there's more clicker questions in the second half than the first, so. Okay. And did you get yours, Sarah? No. Okay. All right, here we go. Our answers were, I have this one showing percentages. Out of 11 respondents, 55% said, and 18% said this one, and 27% said this one. Now, we haven't used the term paradigm, so it wouldn't be that one because we haven't used that term.
Wow.
A paradigm is a framework of how you view things. Not one person said hypothesis, which surprises me, but you were correct in not choosing it. A hypothesis, what is it? Okay. It's an educated guess, and we had here that it's been, well supported. So clearly it's not a hypothesis. And I'm glad everybody understood that, the educated guess versus well supported. So that only leaves these two as options. And I'll go to the incorrect one. Model was incorrect. What is a model?
Model is not true.
Well, it's not necessarily true. It doesn't have to be false.
But isn't a model a theory?
No. A model, the best word for model is an analogy. Something like the idea of a sphere with the stars on it. We know the stars aren't on the celestial sphere, but it's still a model we use because it's useful for explaining how things work. So it doesn't have to be wrong. The celestial sphere model is clearly wrong, but it's something that it's an analogy that makes it easy to think about the situation. So the correct answer was indeed a theory, well supported, applies to a wide variety of circumstances. Those are the important keys to identify, oh, this is a theory. And if it was a narrower, then it would be like a principle, but we didn't actually focus on the word principle, didn't figure it's that important. Okay, oh man, I apparently forgot to take the color codes off of here. Don't worry, none of those color codes tell you which one's right. What is the importance of the equinoctial color?
What? Oh, color.
I talked about it in the first half of tonight. Okay, I'll read them for you. It is the equivalent of the equator on the celestial sphere, or it is the equivalent of the international date line on the celestial sphere, or it is the equivalent of the Tropic of Cancer on the celestial sphere, or it is the equivalent of the prime meridian on the celestial sphere, or finally, it is the equivalent of the Arctic Circle on the celestial sphere. For the lab final, you have to know this answer. That's part of the lab final. Once again, I have these in percentages. I think it's going to be percentages for the rest of the way out. Holly? There we go. Okay. Now I've got to click back on here, believe it or not, to make it stop. So we had no majority this time. We had 18% said A, 27% said B, 0% said C, 45% said D, and 9% said E. Is that a good or bad sign? Well, the answer is, and once again, there's really no two ways of going around this. It's just going straight to the answer. The answer is D. The equinoctial color is where we measure zero right ascension from. The prime meridian is where we measure zero longitude from. So they're equivalent to each other, but one on the celestial sphere, one on the Earth. So it's for measuring going around the equator, how far you've gone. And like I said, that is something you have to know on the lab final. It's not like, we may never see this again. You know you're going to see it on the lab final. On the lab final, you have to point it out and describe its importance. Okay, we're going into history of astronomy now.
Yay.
So we're going to be learning some things that are right, some things that are wrong, that were believed in the past, and how our knowledge has developed to where it is today. Because the scientific process is one of refining knowledge. So we go back to Aristotle, who lived over 300 years before Christ, and he concluded that the Earth has a spherical shape. How did he determine that? He looked at the shadow of the Earth on a moon during an eclipse and saw, hey, there's some curvature to that. And furthermore, he noticed that you had things in the sky that were visible in northern locations weren't visible in southern locations. So you can't just be going flat you have to be going around a bend so you can't see those anymore. And so he had these two lines of reasoning saying the earth is a sphere. So Aristotle, over 300 years before Christ, said the earth is a sphere. It's a ball. I swear I deleted all these. I must have done something wrong. Once again, it doesn't tell you what the right answer is, although you can see, what other people answered last year before I reset this. If Aristotle determined that the earth was spherical in 350 BC, who thought the earth was flat in 1492 when Columbus sailed the ocean blue?
Oh.
I really wish that I know I went through and deleted them, but I also know that PowerPoint crashed after I did that, and I only changed the one that I hadn't changed. It must have been everything above that went back.
So we got to answer it now?
Everyone but Lena and Dylan.
I see.
Okay, now we're all in. And so our answers were, we have 9% here, 9% here, 0%, 0%, 82%,
Oh.
0%, and 0%. They should have, because that was the correct answer. Columbus knew that the earth was round, just like Queen Isabella and everyone else.
They wanted to go around the earth to get into
Yeah,
it.
he thought that he had found, he was extremely wrong in his reckoning for the radius of the earth. And he thought that he could find a shorter passage by going the opposite direction, but everybody knew the earth was round. So where do we get this whole idea of Columbus saying, the earth is round, I have a new and novel idea? It comes from a book written by Washington Irving, who just kind of made it up. And so, truthfully, probably no one is the best answer to choose, but Washington Irving is the one who made up the myth that, like Queen Isabella and people, thought that the earth was flat. Because they didn't.
Well, then he didn't think that the earth was flat in 1492.
That's right.
But sea
That's
captains
why
didn't
no
think that.
one.
Yeah. The sea captains knew the earth was spherical.
They just didn't know how big
Yeah.
it was.
And the thing is, they should have. They should have, because that was actually determined by Aristarchus. Or not Aristarchus, it's going to be, well, we'll see. I've got the name. I think it's like Aristotle. Yeah, I can't even say his name without reading it. But Aristarchus, about 30 years, roughly, after Aristotle's discovery that the earth was spherical, did some measurements. He used the relative size of the moon to the shadow of the earth and the relative size of the shadow of the moon to the earth to determine that the moon must be about 1/3 as big as the earth. And it's actually about 27% the size of the earth. That's pretty good, right? Yeah, that's definitely good enough for me. I'm like totally impressed. All he had to use was, a slide rule, basically sticks with marks on them, and you can slide them around, and things like that. It's pretty crude instruments they had, and he made a really sharp deduction. He also estimated the distance from the moon to the earth, and he came in units of the size of the earth for it to be about 70 times the size of the earth, or the radius of the earth. And it's more like 60 times, but once again, to me, that's close enough. That's really darn good. So, I look at Aristarchus, and I'm like, wow, that dude was totally genius. He wasn't perfect, though. He went further and tried to estimate how big the sun was and how far away the sun was now that he had this information on the moon. And he said that the sun is about 7 times bigger than the earth and about 20 times farther away than the moon.
Close enough.
Not close enough. That one was way off. Hey, no one's perfect, but he did some really, really good work. Now we get to eras. Oh, wait, no, we don't yet. Things about what's moving. It was posited by Aristocrates. Now I've got two people's names mixed up. And I can't remember the name that I started with. The one we've just been using, Aristarchus. Aristarchus finally said that the earth is going around the sun. Based on his observations, that was his conclusion. The earth is going around the sun. Now remember, this is still more than 300 years before Christ was born. The idea of the earth going around the sun. But other philosophers said, nay, nay. Okay. John Pinette, may he rest in peace. They said, that doesn't make any sense because I know when I'm moving. Right? I know that when I'm in the chariot and I'm moving, I can feel the rumble under my feet and I can feel the air blowing in my hair. And I stand on earth and I don't feel that rumble under my feet and I don't feel the air blowing in my hair. Furthermore, if the earth is moving, then we should be able to look at the stars and see shifts in the positions of the stars because of the earth's position shifting as it goes around the sun. They said we don't see those shifts. So the earth must be stationary. That shift in the stars that you would see, here's a prime example. Let's say I'm looking at Kendrick. And so if I'm looking at Kendrick, I'm looking at this angle. I'm looking just to the left of Lauren Lee and to the right of Cody, right? Cody Hagen, right? Yeah.
No, that's Dylan.
Dang it! I will get your name straight. Okay, Dylan. Now I come over here. I've moved. And now I look at Kendrick again. And now he's just to the right of Dylan. So over there, he was to the left of Dylan. Now he's to the right of Dylan. Kendrick didn't move. Dylan didn't move. I moved. And we call that apparent change in position parallax. And so when they were looking at stars, they didn't see stars appear to move relative to others. And they conclude that must mean that the earth is not moving, that it's stationary. So we had the idea of the earth orbiting around the sun way before Christ, but it wasn't largely accepted because they thought they had good scientific evidence. Of course, they didn't really have science as we know it today, but good data to say, no, the earth is stationary. Now, Eratosthenes. Eratosthenes, this is now getting to at least less than 200 years before the birth of Christ. Yes, sir.
I'm still confused by why they thought that the stars were not moving.
The biggest key, I mean, there were obvious things. They didn't feel any signs of motion. But even absent that, the fact that they didn't see any evidence of one star moving with respect to another in a periodic variation.
Oh, okay.
You know, they know we have a year, so if the Earth was going around the sun a year, they'd expect to see nearer stars compared to farther stars look like they're going like this.
Right.
But they didn't see that.
Okay.
Now,
Motion is called parallax, or the
the apparent motion of the nearer star with respect to the farther star is called parallax. It's if you've seen old analog dials, the quality things have a mirror behind the dial. And that's so when you look at it, you look so you have the dial, and then you see the reflection on itself, so that you know your eye is above it and not over to the side. Because you'd have that same parallax go over to the side, it looks like it's a different position than if you're straight over. Now, the answer to, they didn't see that, they concluded there was no motion. It's because they were looking with the naked eye, they couldn't discern the very small motions because the stars are very far away. Now, using our modern day telescopes on Earth, we can identify somewhere in the ballpark, I think it's around 2,000 objects where we can measure parallax from Earth. And using the Aristarchus satellite, we can measure many, many more than we can measure from Earth, the parallax. So we now see the parallax, a sign that the Earth does move. You had a question, Ken?
So the parallax is not the position. Like you had a slide up the last slide over.
Yeah.
It's not the lines.
It's the fact that when you see this star here, it appears to be over here compared to those background stars when the Earth is on this side of the sun. But on this side of the sun, it appears that it's moved all the way over there. So compared to the stars, you think that it's moving back and forth.
When it's really the Earth.
When it's really the Earth going around the sun. But they didn't see any of this back and forth motion. And since they didn't see that back and forth motion, they concluded the earth must not be moving.
So parallax is just that optical illusion of the stars.
Yeah. Okay, so what did Eratosthenes do? Eratosthenes noted that in the city of Syene, at a certain time, he saw sunlight going to the bottom of the well. So you have a vertical shaft, and if sunlight hits the bottom of that vertical shaft, the sun must be directly over that shaft. And so he said, aha, I know the sun is directly overhead at this time of day, at this time of year. By the way, I don't know if you guys have ever seen the movie National Treasure. It just busts me up that they look at the shadow at a certain time as an indicator of where they should be looking for the treasure. Because you have to have the right day of the year as well for that to actually work. If you don't have the right day of the year, the shadow points a slightly different place every day at the same time. But hey, astronomy, we've already seen the fractured astronomy in Apocalypto. So he makes this notice, and so he says, hey, I'm going to have my buddy over in Alexandria, which is about 7 degrees away. Well, he didn't know it was 7 degrees away yet. He just knew how far it was from the city of Syene to Alexandria. But he had his buddy in Alexandria, for which Alexandria, Virginia is named, measure the angle of the sunlight by using the shadow from the obelisk in Alexandria. And he said, well, when you said the sun was right overhead at Syene, it was 7 degrees off here in Alexandria. So he says, okay, it's this many, well, he didn't have kilometers then, but it's this far to Alexandria, and we had 7 degrees, which is, of course, 7/360th of a full circle. And from that, he said, okay, the full circle would have a distance of 2 pi times the radius going around the circle. And so if we have 7/360th of that, boom, calculate the radius by knowing how far it was from Syene to Alexandria and knowing that angle. And so he came up with the diameter of the Earth that's 13,000 kilometers. What's the actual diameter of the Earth? Somewhere around 12,750 kilometers. Pretty darn good. Well, his method was really, really good. Very simple method. And so the size of the earth was well known 250 years before the time of Christ. It was known that it was a sphere. It was known that it exactly almost what its diameter was. So now you go to Christopher Columbus and you're, okay, so Columbus probably didn't study well enough because he should have known how big the earth was and been able to do the calculation about the potential savings in distance trying to go to India the wrong direction. But, he missed on that part. Yeah. We can then give him credit instead of the Vikings for, because clearly the Vikings were in North America before Columbus. You guys all know that, right? Yay! Or his father, Eric the Red, actually. Okay, so here is where we talk about the angles. We measure things in angles. I've mentioned that before. I mentioned earlier tonight that the size of both the sun and the moon as measured in an angle is about half a degree, which is the reason why we can have annular eclipses or full eclipses. Annular eclipses is when it looks like an annulus. That is, you have a ring. So an annular eclipse, it's dark in the middle, and then you see the sun all around it. And that would occur when the angular size of the moon is smaller than the angular size of the sun, which means the moon is farther away from the earth than normal, and the earth is closer to the sun than normal. And we've reached the halfway point through the slides that I had prepared for tonight. We're not going to go through all of them. Like I said, I don't intend to go through all of them. This here is a very important equation for us in astronomy. It is a way of determining angles and, relating angles and distances. This is actually essentially the equation that Eratosthenes used for determining the diameter of the earth. So this is just using geometry. You have a circle that has 360 degrees in it. Do you remember why I said there were 360 degrees in the circle last week?
Because number of days in the
Yeah,
year.
roughly the number of days in the year, and they're just saying, ooh, but 360 is such a magical number. So we have 360 degrees in the circle. You have the radius of the circle here, which is conveniently marked D for distance. And we know that the circumference of a circle, circumference, is equal to 2 pi times the radius. This is actually the definition of pi. Pi is defined as the ratio of the circumference of a circle to the diameter of the same circle. And some people will point out that in the Bible you can find a description of some ceremonial vessel that was something like 10 cubits in diameter and 30 cubits in circumference. And of course, if you do your math, that tells you pi is 3. And then some people will say, well, those Bible people know, they didn't even know pi right. Of course, then you say, well, what did you expect? You expect to say it was 31.4 cubits? I think they were just taking rough numbers. I don't see it as some significant mathematical error. But that's how you get the definition of pi. Interesting point of fact. The state of Indiana, back in the 1800s, some genius decided to try to make math simpler for grade school students. Grade school students had to learn all of these crazy rules involving pi for circles. And so he introduced a law that said something on the order of, let the ratio of you've got things like quadrant for fourth and this and that. But basically, he wanted the ratio for the circumference of a square to the side of one side of a square to be the same as the ratio of the circumference of a circle to the radius of the circle. And when you put it all together, you came up with, I think it's the radius. Anyway, when you put it all together, that law would have set pi equals 4. And unlike Nebraska, or like every state except Nebraska, Indiana has 2 houses. And the first house passed this resolution unanimously. It was going to make life easier for the school children, because none of those politicians knew any math. And then somebody said, wait a minute, you realize what you're saying is this fundamental constant is going to be equal to 4 according to your laws. And so it was never brought to the other house because people realized we can't make a law to change pi to a different value that makes no sense. Just an interesting trivia thing about pi. And the state of Indiana, well known for the mathematical literacy. Speaking of mathematical literacy, let's get back to this. We have the circumference of a circle is 2 pi times the radius. Now, if we have an object and it has a diameter of the object of L, and we measure the angle of that object A, then we can relate the angle of the object, divided by the total angle for a circle, 360 degrees. That doesn't look like a 6 yet. That ratio of angles should be equal to we call this, the diameter here, but it's the diameter of the object we're looking at, so I'll put the object diameter to the radius of the circle. Not the radius of the circle, the circumference of the circle. Right, so if this takes up, let's say, 7 degrees, such as what Eratosthenes did, then it would be 7/360ths of the complete circle. And it would be whatever that distance was divided by the circumference of the circle. So if we take this, we can then say, well, the object's diameter, I usually want to know that. The circumference relates to the radius or as it's called here, d for distance. So I replaced circumference with 2 pi times radius. Object diameter is a over 360 degrees. So now I can either solve this for the angle if I know the diameter, or much more commonly, we measure the angle, we want to know the diameter. And so we can say that the object diameter is equal to 2 pi times the radius, which is the distance away, over, times a over 360 degrees.
How
So-
can people back then know how far things were away from them?
Well, it can be hard, right? What Eratosthenes did was he measured the angle and he measured the distance on the surface of the Earth, and then he found what the radius was from that. These days, we're going to be doing things much more along the lines of finding what this radius is, which is going to be the distance away. So if I take this and I solve it for radius instead, so the distance of an object away is equal to 360 degrees over a times the diameter over 2 pi. Right? I just solved that for radius. I divided by 2 pi, multiplied by 360, and divided by a. So,
They know how big the moon was.
well, the Aristarchus, for instance, had determined the size of the moon from his comparisons of the radii of the shadows during eclipses. Now, I worked out here a variation on the math, the way that, oh, come on. The way that we're usually going to see this, this L is the distance away, the second equation I did. And hopefully that looks like the second equation. 2 pi times the diameter of the object times the angle divided by 360 degrees. Hopefully that's exactly what I wrote here, because actually that looks opposite, doesn't it? 360 on top and 2 pi on bottom. I must have made a mistake. Either that or I just can't remember from one moment to the next.
360 on.
Well, this here has 360 on top and 2 pi on bottom, but this one here is the opposite. Diameter. Yeah. Okay. This is the first one that I solved on the other page. And then here I changed it to the way of the second one, and so that's why that one looks the same. Or actually, no, this is solved for angle. You can solve it for lots of things. The reason I did this math here is we call this in this form the small angle equation. And in here I have some conversion factors that you probably don't know. 360 degrees divided by 2 pi. Degrees are actually a conversion from a natural unit. The natural unit is there are 2 pi in a circle. We say 2 pi radians to indicate that it's the natural unit for angle, but there's actually no units to a radian. A radian's unitless. And a degree is made up of minutes and seconds. Simplest question I'm going to ask tonight, besides how many days are there in a week, how many minutes are there in an hour? 60. How many seconds are there in a minute? With angles, we have the same divisions. So there are 60 minutes in a degree and 60 seconds in a minute of angle. So we measure angles in minutes and seconds, just like we measure time in minutes and seconds. How many people knew that? Okay, we had 3 people who knew that. That's actually pretty good. So these here are the conversion factors to change from degrees to seconds of arc. A second of arc is 1/60th of a minute of arc. A minute of arc is 1/60th of a degree. Question?
This is related to where the sun is, right?
Well, this is going to be used for things to say, okay, we look out here and we see Mars. And Mars makes up this big of an angle. And if Mars is this far away, how big must Mars be?
Right.
And we do those kind of calculations all the time. The calculations that were just made on Pluto's size were made now because we were close and able to take a photograph from much closer and make a better estimate. But from here on Earth, that's exactly what we did. We can calculate how far away it is, and we can measure how big of an angle it makes. And then using, yeah, I know the battery's low. Using this equation, then they determined what the diameter of Pluto must be. And it turned out that they weren't right because they didn't know as much about the atmosphere of Pluto as they thought they did, and it turns out Pluto's bigger. But that was a correction on the equation based on atmosphere. So that's an example of where it was used until 2 months ago now. Okay, so that equation is going to be important. You're going to have problems where you're asked to relate. I got to go back. Where you're asked to relate the angle in arc seconds to the diameter of the object and the distance away. So make sure that you remember this equation. This number here, 206,265, that's just the result of this conversion factor between degrees and radians. So 206,265, just a constant from a conversion factor. It will turn out that when we define an arc second, a parallax arc second, also known as a parsec, we use this equation, and 1 parsec is equal to 206,265 astronomical units. That number will come into play again because we're using that equation to define it. Okay, moving forward. I know, it's math, and most people in this class are like, I don't like the math. I really appreciated Pastor Lemon today talking about seeing that stupid sign, another day passed, and I didn't use algebra. I actually muttered under my breath, or maybe not so softly, that means another day of being an idiot. But you do use math every day. True story that would embarrass my wife. We were talking to a financial planner, and the financial planner said, oh yeah, I can sell these stock and we'll just charge you, and I forgot what her exorbitant fee was, something like 5%. And my wife said, oh yeah, that sounds fair. Well, let's hold off. And then after going, I'm like, honey, you realize that that's going to be this huge amount of money she's charging us just to sell, the stocks. I had no idea it was that big. All you got to do is multiply this number by that number. That thinking part is what Pastor Lemon was referring to, using the reasoning skills. I really appreciated that. All right. This is a new idea moving forward, so not tied to the last one. If you look at the planets in the sky, it turns out that all the planets orbit the sun in very close to the same orbit that the Earth follows. We take the plane the Earth orbits the sun as our standard measure. Everything else is how far away it is from our plane. And except for Mercury, they're all extremely close to us. Mercury's is tilted a little more, but Mercury's also really close to the sun, so it doesn't get that much below or above us still. So pretty much all the planets go in the same plane. Pluto, by the way, not a planet, so my statement is factual. Pluto is also tilted by a fair amount because it has a really big orbit. It does go fairly far below and above our orbit. So because all the planets are pretty much in that same plane, if you look up in the sky, they all appear to be going on the same path. And so you can look up in the sky and see the planets forming what looks like a line. And of course, the spaces change because they have different periods. But you'll always find them on that path that the sun appears to follow. And what do we call the path the sun appears to follow? We call it the ecliptic. So they all fall very close to the ecliptic, which means that they are in the zodiac constellations. Because the signs of the zodiac, those constellations, are the constellations that the ecliptic is going through. So when you're looking for planets, the planet is in, the house of Sagittarius. I don't know. I don't know how they do astrology. I just never studied it. I'm not sure if that's a good thing or a bad thing. As a person teaching astronomy, it would be good to know a little bit about what they're doing just so you can, speak intelligently. Geocentric models. This here is a model, a framework for thinking about things. Except for, I believe Aristotle thought this to be true. Aristotle believed that all of the planets were fixed on crystal spheres. And each one of those crystal spheres was rotating about the Earth. And there were interesting axes to connect one to the next and one to the next with gears. And you had the prime mover that was basically this outer one that goes around and makes all the rest of them move with fixed rates based on the gears between the spheres. And you have the celestial spheres, the outermost of these spheres in Aristotle's model. All the stars are on the celestial sphere, and then the planets are inside. Now that brings up, what is a planet? Historically, the word planet meant wanderer. So the planets were the things that they did see moving relative to the stars. And you might instantly go back to me talking about parallax and say, "What? I thought you said they didn't see parallax." Different motion. The planets typically each night would move just a little bit further and would go all the way around. And so those were wandering around in the sky. They didn't go back and forth on a yearly basis. They just kept going around in circles. And so planet just means wander. They're the things they saw that moved against the sky in a continuing pattern. Now we'll see they didn't just continue to move. There's what we call retrograde motion. I don't want you to think, teachers just know about retrograde motion. What kind of moron is he? I do. So, do you have a question? No, okay. So this is essentially the model that Aristotle had. You got all these crystal spheres. He believed they were crystal because he thought crystal was the perfect material. Now, a lot of people don't even know what crystal means. A lot of people would say, no, that's not crystal. But they'd be wrong, right? This is crystal. It's just iron crystal. When he was talking about crystal, though, he was talking about quartz crystal. Like what?
The pretty stuff.
The pretty stuff, okay. And I swear I'm going deaf, so it doesn't, yeah. So he believed they were crystal and spheres because he thought crystal was the perfect material. He thought they were spheres because he had been taught that the sphere was a perfect shape. Not a lot of science in this model, right? Based on pretty ideas. And Aristotle believed if you had a really pretty idea, it had to be true. Now, unfortunately, his model had some significant issues. The most significant issue was this thing we call retrograde motion. So if you watch a planet move, it typically is just moving from west to east as you observe it from one night to the next. But, and I may have cut out the slide that shows the picture. I did. I cut out the slide that shows the retrograde motion. If you watch this motion, it will go like that and then continue on like that. Well, this part here was going the wrong direction. So it's like the planet was moving across the sky from west to east, and then all of a sudden it stops and goes back toward the west, stops again, and then continues going east. Now that's kind of hard to explain, isn't it? I mean, why would the planet stop, go the opposite direction, and then go forward again?
Because Siri told it to make a U-turn.
So this retrograde motion was a problem that was realized right away. Enter Ptolemy. Claudius Ptolemy, I believe is his name. Ptolemy said, hey, I can come up with an answer for that. So Ptolemy, now notice this is, I put CE, that comes from the textbook. Let me change that to Anno Domini. Ptolemy, who lived 150 years or so after the birth of Christ, he said, if we take his model and we modify it just a little bit, I can explain retrograde motion. Retrograde motion is that period of going backward. And what he said was, we have the planets on spheres, but the big sphere has a little sphere. And I start here going, big wheel run by faith, little wheel run by the grace of God, a wheel, a wheel. Anyway, you have a big sphere and a little sphere. And the little one is doing these circles as it goes around the big one. And so these little circles are called epicycles. You see that there, epicycle? So you have the little circles as it's going around the big circle, which is the deferent. And so if you look at this picture here, and I'll zoom in on the picture. As you zoom in, you see that it's going forward up to this point right here, but then it's going backward, retrograde from there to there. And then it goes forward again until we get to here. And so the red there is the normal motion, and then I will use blue to show the retrograde. And so this idea of the epicycle with the deferent allowed him to explain retrograde motion. Now it's a pretty complicated little picture, but it worked. And it didn't fundamentally change the ideas of Aristotle, it just fine-tuned them. Now there were some other fine-tuning things, like he said, okay, yeah, the Earth is the center of the universe, but actually the center of those spheres is offset. You have the Earth here, and then you have another point here that's symmetric about the center of the universe, and they're all going around this. That was to account for some other variations in the orbits. So his model is just a little complicated, a little convoluted, but it predicted the positions of the planets quite nicely. And so people said, okay, I have this model, this at that point we could say a theory. I have this theory about where the planets should be and why they're there, and it makes predictions. Now remember, with the scientific method, which also hadn't really been developed then, you observe something interesting like we have retrograde motion. You come with a hypothesis, an educated guess, to explain why it occurs. His educated guess is, well, we have these little circles on the big circles. And then it makes predictions. In this case, it makes predictions on where the planets will be at any given time. We make a test of that prediction. We make measurements of where the planets are based on the predictions of this model, and they're correct. And if our predictions are correct, we develop more faith in the hypothesis. We start modifying it, well, not modifying, elevating it to being a theory after it's had a fair amount of testing. It's never a proven thing, but we get more and more confidence in it. And so scientists got great confidence in this model. Although over time, its predicting power got, here's the picture with the actual retrograde motion. So I had it there just a little later. Over time, the predictions started getting a little flawed. And so a lot of scientists, people like Tycho Brahe, spent a lot of time trying to figure out how they could fix it to make it so it was more accurate. Nicholas Copernicus is the one who gets the modern day credit for a theory that Aristarchus had had. Aristarchus said that the Earth went around the sun. But people had rejected it because they didn't see parallax. Now, Copernicus also championed the idea of the Earth going around the sun. Little problem with Copernicus. Copernicus was a Polish canon. I like to think that Sebastian Janikowski, the Raiders place taker, is a Polish canon because I can't relate, he's Polish. A Polish canon, basically, he was kind of like a priest. And he knew that it would cause problems in the church for him to say that the Earth went around the sun. Why would it cause problems? Because Aristotle's model had the Earth as stationary. And Aristotle held that the earth was imperfect. It was flawed. We have sin. We have people that go out and kill people. You guys probably saw the dudes killed a police officer up there in Ohio today. Yeah. Yeah. You know, I mean, things are going crazy. We have lots of bad things happening in our world. It's flawed. But Aristotle said, but if we go out there, it's perfect. And in fact, we can look and we can see the moon isn't a perfect sphere. It's got things on it. He said, well, that's just because it's so close to the earth that the earth's imperfections have marred the moon. But if you go further out, it's perfect. And so the Catholic Church took this idea and they said, aha, we have the heavens above. Heaven is a perfect place. We have hell below. Hell is where sinners go. And so the earth has to be the center of the universe, and hell is under the earth, and heavens are up above us. And any theory that conflicted with that would be conflicting with the Bible, was their interpretation. So they interpreted the Bible to match, now of course Aristotle wasn't a Christian, right? I mean, he lived before the time of Christ. But they interpreted the Bible to match the scientific understanding of the day, but then it became part of the dogma, and changing dogma is challenging to a religion. And so he didn't want to challenge the religion. So he hand-wrote pamphlets. I mean, what's he going to do? Did they have the printing press, available to everyone? But he hand-wrote pamphlets and anonymously passed them out to people for them to consider his ideas of the planets, including the Earth, doing orbits around the sun. And just before his death, he did finally publish it. He's going to die now. I guess it doesn't matter now if the church hates me. And so he did publish it, and he is known for bringing it back. Now, his model had the planets doing perfect circles around the sun. It explained retrograde motion in a very simple way. If this was next week, we would have just done a lab simulating this instead of having lectures with the bad weather. So if it's bad weather next week, that's what we'll be doing. But I had to introduce it first before we do the lab on it. So it was very simple. Whereas, remember, Ptolemy's model was very convoluted. You guys know what Occam's razor is?
I don't know, but I've heard of it.
I do? Occam's razor. Occam's razor is a simple tool for trying to decide which idea to believe. Occam's razor is if I have two different explanations that explain the same thing equally well. That the one that's more likely to be true is just the simpler one, the one that involves less complexity. So using Occam's razor, we have Copernicus' model that everything's doing perfect circles around the sun, or we have Ptolemy's model, based on Aristotle's model, that we have these crystal spheres, and on the crystal spheres we have smaller wheels, epicycles, and those are all going around to make the patterns, and we're a little offset from center. More complicated model. Neither one of them made perfect predictions. They made about equal quality predictions. So if they make equal quality predictions, Occam's razor says you're going to take the simpler one. But of course, humans are not perfectly logical beings. The humans said, we have had Ptolemy's model for well nigh 1,500 years now. Closer to 1,800 years. I believe this, my parents believe this, their parents believe this, everyone that's ever lived, as far as I'm concerned, believe this. I'm going to change to a competing model just because this new pollutant guy thinks he's, just as good? No, I'm not going to change. He's got to show me. And so people did not accept his model because it didn't make any better predictions. But it will become accepted, and he's the one who revitalized the idea, hence we give him the credit. His methods were based on measurements using positions of planets. And here we have a bunch of vocab words. And I'm going to break down, I have like 4 slides that have this picture with a different vocab word on it. So I'm not going to stay on this slide just because I want to go to each individual slide with the vocab words. But notice the vocab words. We have quadrature, opposition, inferior conjunction, superior conjunction, and conjunction. So let's look at these words. Opposition. Opposition means you have an object that's on the opposite direction as the sun. So the sun is pointing, well, right now the sun's pointing, I don't know, somewhere down there, right, to get to the sun. Something in opposition would be the opposite direction. So if you look here, if we're on Earth, if we had Mars right here, that would be in opposition because Mars would be in this direction and the sun in that direction. It's a simple term, right? Easy to understand? Vocabulary word that you want to add to your vocabulary. So opposition can only occur with planets that orbit farther away from us than the sun. Superior. You probably heard this quote. It was used in Periscope. Not a superior officer, just a higher ranking one. Superior means above. A superior planet is a planet that orbits farther from the sun than we do. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus. Yeah, I did. See, now I put Neptune there instead of Uranus, Neptune. Okay, there we go. Of these planets, here's the Earth. Which ones are superior? All of these are superior. So what do you suppose we call the other ones? Yep, inferior, because that means below. So these here are inferior planets. Keep in mind when I say a superior planet or an inferior planet, it's not saying a better planet or a worse planet. It's just saying farther from the sun or closer to the sun. So which kinds of planets can have an opposition? Only superior planets can have oppositions.
So why is superior conjunction on the same circle line as inferior?
It's not a superior planet. It's superior because it's the larger conjunction. Inferior conjunction is the smaller conjunction. So it's still using it to mean bigger or smaller, but it's not superior planet, it's superior conjunction. Okay, so we have the opposition. Only one type of opposition occurs with a superior planet. Now we have conjunctions. Conjunction means if I look toward the sun, I have the planet on that line. So it's a straight line, Earth, sun, and that planet. And you can have the planet between the Earth and the sun. That's closer than the sun. And so it's an inferior conjunction because it's closer than the sun. If we have the planet on the opposite side of the sun, then it's a superior conjunction because it's farther away than the sun is. But it's on a straight line with the sun from the Earth. Not in opposition, on the same side as the sun. So superior and inferior, yeah, my battery, we have to stop within about 10 minutes because my battery will be dead then. Superior and inferior planets are superior and inferior conjunctions only occur for inferior planets. A superior planet can have a conjunction but only has one type of conjunction, the one that would be considered a superior if it was an inferior planet. And I know, throwing around so many inferiors and superiors gets confusing. But superior planets just have conjunctions. Because a superior planet only has one type of conjunction, we don't have to name it a superior conjunction. So we have conjunction 3 times here. The 2 that I've circled in red are the kind that occur for inferior planets, and for superior planets we just call it a conjunction. I could change, actually I'll keep it that. So we've talked about oppositions and conjunctions, both having to do with straight lines, but opposition is opposite direction, conjunctions are on the same side. Then we have quadrature. Quadrature is when it's a right angle looking at the sun compared to looking at the planet. That can only occur for a superior planet. You can't have an inferior planet on the line that's going like this. And the quadrature is important because that's actually what Copernicus was using. Copernicus used the times for quadratures of different superior planets to estimate their distances from the sun, and was actually very accurate with it. This will be, I think, our last clicker question. What term is used when Venus passes between the Earth and the sun?
Oh, snap.
It's funny because I have the wrong answer marked as correct here.
Really?
Yep.
I thought we would know that.
Well, yeah, you don't know which one's marked correct here because you don't see that anyway. I was looking at the answers, and all the answers it was saying were wrong, and I'm looking at, no, I think that's right.
Hold on. When Mars passed?
When Venus passes between the Earth and the sun.
Hold on, try to visualize. Alright, hold on then. Alright.
You see how many times?
I just, the color changes each time you do it, and after 4, it cycles back to the original color, so.
So like 4 times.
Okay, so our answers here were 8. Oh, I'm still in white. Surprisingly enough, you can't read white on white. 8, 1, 2, 0, 0. Now,
I think that.
keys to answering this, passes between, right? So passes between means that you have, here's the Earth, here's Venus, and here's the sun in a straight line. If it's not on the opposite side, it's not an opposition, it's a conjunction. So it had to be a conjunction, so it had to be one of these 3. And then we just say, okay, oops, one of those 2.
Okay.
One of those 2, and then we say, okay, superior. Was Venus farther away than the sun?
It was fine.
Nope. It was between, so it had to be inferior conjunction. Oh, good. I'm not grading if you're right or wrong. I'm asking you to put your answers out there so you can see if you understood or not.
Oh.
Okay. So things that were discovered by, that were observed by Copernicus. One piece of evidence used by Copernicus was the elongation. Another vocab word that I didn't put in red here. Elongation is the angle from the horizon to where we see a planet. And the elongation for Mercury is never greater than 28 degrees. Mercury is always seen within 28 degrees of the horizon. And the elongation for Venus is never greater than 47 degrees. It's never seen more than 47 degrees from the horizon. Now, if the Earth was the center and Venus was going around, that wouldn't really make sense, right? It should go all the way around. We should see it all over the sky, not just on the horizon. So in Aristotle and Ptolemy's models, they actually had a line pinning from the Sun, Venus, and Mercury, and their epicycles were along that line that pinned them to the Sun. So that explained their smaller elongations. But there's a piece of interesting evidence that required another oddity in Aristotle's and later Ptolemy's model. And then Copernicus looked at the quadratures, and from those calculated. So here we have Copernicus's calculated distances from the sun to each planet measured in astronomical units. Remember, astronomical unit, distance from the Earth to the sun. And here's our now understood values. Notice these are different by 0.01 astronomical unit. Those are the same. Of course, that's by definition the same. Those are the same. Those are different by 0.02. Saturn is the only one that's not super, super close. So these measurements that Copernicus made were actually really, really darn accurate measurements that gave us the distances to the planets. And yeah, I'm going to start the next lecture with this slide on the Copernican revolution. So we've talked a little about Copernicus, and then we'll go further into Copernicus next class period. Any questions before we close up for the evening? It's super hot in here, and I'm sorry, but hey, we're done and you can go home where it's not so hot.